Hi everyone, I'm Valentina Rossi, Corporate Marketing Specialist at Zappi Group. Welcome and thank you for joining this technical session. Just a quick reminder that this session is being recorded and will be available on demand after the session. If you have any questions, feel free to share them using the Q&A tab on the right side of your screen, and your question will be sent privately. Today's topic is quite technical, but we will approach it in a practical and accessible way. It's my pleasure to introduce our speaker, Edward Jones from Infineon, and Edward will guide us through GaN, bidirectional switches, and explain how they are enabling new and innovative approach to electrification. Welcome, Edward, and over to you.
Thanks, Valentina. So as she said, I will be going through this new GaN bidirectional transistor technology and how this is already impacting e-mobility and electrification overall, as well as a number of other applications. But I think I'll focus a lot as well on what we can expect to see going forward. So it's a trend that's really just getting started. So I'll go through. I hope to finish early enough that there's plenty of time for Q&A. But I'll go through some fundamentals to start. What is the bidirectional switch and why does it work the way that it works? I'll go through a few different types, which have different use cases. And then I'll really focus primarily on how this applies to power conversion, things like onboard chargers for EVs and motor drives. So what are we going to cover today? We're going to cover what are bidirectional GaN switches. The first thing people normally wonder is why is this suddenly a thing with GaN? You know, the 4-quadrant switch has generally been considered something ideal for, chapter 1 in a power electronics textbook, but not really something to discuss in practical terms. And we don't see a single bidirectional switch in silicon or silicon carbide. You can, of course, put switches back to back and reproduce the effect. But when we talk about a HEMT, it's important to remember, or when we talk about GaN, that is to say, it's important to remember we're not talking about a MOSFET. So in a silicon MOSFET at, let's say, 650 volts, we're generally talking about a superjunction MOSFET with these deep wells, the source and the gate are on the top of the chip, drain is on the bottom. It should be something like CoolMOS. In a silicon carbide MOSFET, similar, but without the very deep trenches, shallower trenches. Still, though, gate and source are on the top, drain is on the bottom. So this kind of gives you an idea of why it's a unidirectional switch, because the source and the drain are very different. One of them has a gate next to it, the other doesn't. Meanwhile, the GaN HEMT is a lateral device. There's not a whole lot that's different between the source and the drain, so it doesn't take much effort to use it in a bidirectional way. But there are a few different flavors. And these different flavors can be used for a lot of different things. For example, battery charging, battery protection, motor drives. And I'll get into all of these. Now, to start with, before I get into the way a bidirectional GaN switch behaves in the third quadrant, meaning when there's voltage from source to drain, let's talk a bit about how a normal GaN HEMT behaves in the third quadrant. I like to start this explanation by talking about what happens in a very different scenario. Let's consider you have a MOSFET, as you see here in the top right, or a GaN HEMT, as you see in the bottom right, and you connect the gate and the drain together. This is kind of a strange thing to do, but let's just bear with me. Assume that you do this as an experiment, and then you try to force a current into the drain. So try to imagine in your mind what's happening here. Now, there is an open circuit from gate to source and drain to source, but an open circuit just means a junction capacity. So that current is going to very quickly charge up the CDS and CGS and make those voltages rise. But they can't rise forever because at a certain point, the gate is going to turn on. So if we look at the transfer characteristic of that MOSFET or GaN transistor, this dictates the behavior of the switch in the saturation region. That's exactly what we're doing here. We're riding up the saturation region. So if, for example, you force 20 amps into the drain, this is going to charge up BDS and VGS to 2.6 volts. Why 2.6 volts? Because once it gets to 2.6, the gate is on enough that the current's going to actually start to flow through the channel. Then you're not going to have any more charging of these junction capacitors. So using the MOSFET or the GaN transistor in this way is basically forcing it into the saturation region at exactly the current you're trying to force in a state that the channel can't support any higher current than that. So why are we talking about this strange scenario? Because it's actually not that different from what we're doing in the third quadrant in a GaN HEMT, what we would normally call body diode behavior. Now let's consider this very symmetrical device, this GaN HEMT. As I mentioned before, the gate, the source, and the drain aren't that different. So now let's flip it on its head. Let's short the gate and the source together instead of the gate and the drain as we had in the previous slide. Now this is more realistic. This isn't so far-fetched. This is exactly what we do when we're trying to turn off the gate. We short it to source. But now let's consider that you do the same thing as in the previous slide, but in reverse, you force a current into the source out of the drain. This is essentially freewheeling behavior during dead time when you would normally have a body diode to conduct. But again, HEMT doesn't have a body diode. So what happens? Instead, you charge up those same capacitances, in this case, VGD and VSD. They charge up, and as a result, you ride up the reverse saturation curve, the reverse output curve, which is also shown in the data sheet. So kind of like in the previous slide, you would operate the channel in saturation with 20 amps at 2.6 volts, but here it's 2.5, almost the same, very, very similar in forward and reverse. But this is with the gate and the source shorted together. Gate VGS equals 0. This is a very standard way to turn the gate off. But let's say, just for the sake of the thought experiment, that you wanted to turn the gate off with a negative voltage. This is also very common. If you did this with a silicon or a silicon carbide MOSFET, nothing would really change. The body diode would still conduct with the same voltage. But here, you're making it a little bit more difficult for that current because now that current, let's say 20 amps, is going to charge up the SD and VGD, but the VGD is going to have to get a little bit higher to reach its threshold because it's going to have to overcome this -1 volt. So let's say we apply -1. Now the VSD is going to be actually 1 volt higher than VGD. So for that same condition before, 20 amps, instead of 2.5 volts, it's 3.5 volts. So this is another way of saying that the more negative voltage we apply to the gate, the higher the body diode drop, or the VSD, is going to be during the dead time. But that's the bad news. The good news is we can actually leverage this in a very interesting way. So imagine instead of using -1 volt on the gate, imagine we used -100 volts. This would be a little bit strange, but if you apply -100 volts to that gate, then you have forced the body diode voltage, the voltage at which it will conduct, to 100 and 2.5 volts, meaning that now you have a switch that can block 100 volts in both directions if you turn it off with -100 volts on the gate. So this, in fact, is what we're doing when we make a common source bidirectional HEMT. In a GaN HEMT, we typically have the gate very close to the source and very far from the drain. So we scale the distance from the gate to the drain to block the voltage. You're going to find this distance is a lot higher for a 400 volt device than for a 40 volt device, for example. This is not drawn to scale, of course. This distance is very, very big. But if we drew it to scale, you wouldn't be able to see anything. The words would be very small. So you can imagine that if you did what I just explained, you applied -100 volts from the gate to source. Since the device was not scaled that way, you are not going to find that the gate survives such a high negative voltage. So if you want to switch to be able to block 100 volts on the left side or on the right side, you need to increase that distance. And if you increase the distance from the source to the gate, now at this point, then the word source doesn't have any meaning because the drain 1 and drain 2, or the two terminals, are symmetric. The gate is right in the middle. You have the same distance to block that 100 volts on the left side as you have to block 100 volts on the right side. Now, if you apply voltage positively from the left, you're going to be blocking it over here. If you apply voltage positively from the right, you'll be blocking it over here. So you have two different drift regions to block that voltage, which is the same as you would have in a back-to-back MOSFET scenario. But here, at least, we're able to monolithically integrate them together and control them with one gate. So what are some cases where we use these? Mostly, we're going to see this type of common source bidirectional switch in a battery protection environment, in a static switch. One of the reasons is that this technology is very compelling when we go to very low voltages. For example, 40 volts, 100 volts, to protect a 20-volt battery, a 6-volt battery. And it just so happens that all of our cell phones, if we were to pull them out and take them apart, we would find a number of back-to-back 40-volt silicon MOSFETs, which are on the charger input between the charger port and the battery, between inside the battery, most likely, as well as in all the chargers. So you're going to have all these bidirectional switches in series to make sure that you have really secure protection between the devices that are getting charged and the devices that are charging them. We can replace those with a much smaller single switch GaN device. And in this case, save the PCB real estate by 82%. And we're talking about inside a cell phone here, where every square millimeter counts. So this is a very nice use case. It has a high potential to impact electrification, especially for relatively low voltages, like e-bikes, e-scooters, e-motorcycles, that kind of thing. It may impact electric vehicles as well, but there it's a whole other scale, many orders of magnitude difference in current and in voltage. So then how does this apply to the higher voltage? Now, if we take a 650 volts GaN HEMT and we talk about moving the gate to the center, you have to remember, as I said, the scale is way off here. This is a cartoonish drawing so that you can really see the detail. But the truth is that the gate is very far from the drain and very close to the source, almost on top of the source. So if we were to move the source really far away and have two different drift regions to block the voltage in two different places, it would be very large. It would be, the size of back-to-back MOSFETs, but not in a very compelling way. So we have another trick here. For this higher voltage, instead of moving the gate, we add a second gate. Now, this gate 1 is very close to this source 1, which is what we were calling over here the source. But gate 2 is very close to what we were calling the drain, what we're now calling source 2. We got rid of the name drain here because, in fact, the voltage can be blocked from the left to the right or the right to the left, just like in the previous example with the common source. But this way, it's a little more interesting because we have one voltage blocking region, one drift region in the middle. And at the 650 volt node, the difference between a device with a single gate or a device with two gates is quite small. It really doesn't add much size to the device, much complexity. So it's almost a free lunch, really. You get the second gate. Now, what do you do with the second gate? You have here 4 distinct modes of operation, which really are the same as what you would have if you took 2 MOSFETs and you put them back to back connected at the drain, hence the name common drain BDS. If you turn both the gates off relative to the two sources, gate 1 off So 0 volts relative to source 1, gate 2, 0 volts relative to source 2. This is fully off. So it's going to block voltage 650 volts in both directions. Meanwhile, you can turn both gates on. Now you're going to have no voltage blocking, and you'll just have a single RDS on of drop, or in this case, we would call it RSS on because there is no drain anymore. So if it's a 20 milliohm device, then you're going to have 20 milliohms of resistance between the two source terminals if you turn both gates on. Now, we rarely use the fully off state because if the gates are both off and you don't have other parasitic paths through your system or other freewheeling paths, if you have some inductively stored energy and you have no path for it to go, your board's going to very quickly self-destruct. So most of the time, we find that it's the three modes that are used are fully on, or blocking voltage in only one direction with freewheeling in the other, or blocking voltage in the other direction with freewheeling in the first. So essentially emulating the scenario where you've turned off only one of the two back-to-back MOSFETs instead of turning them both off. But that being said, you can use it in a fully off state, and things like a current source inverter, that's very important. Now, what about the substrate? So the thermal pad you see at the top of the GaN package, and I talk here about NVIDIA GaN packages, but the same would probably be true of most other vendors in the marketplace. This thermal pad is the substrate, the silicon backside of the GaN chip, which is primarily just there for mechanical stability. It's just sort of the dinner plate that the GaN, the active GaN area is implanted on top of. But you don't want to have a floating substrate. So the silicon substrate in a GaN HEMT is normally connected to the source, or that is to say, it's normally connected to the lowest potential in the switch, which is generally going to be the source in a unidirectional normal GaN HEMT. But in this case, we've gotten rid of the convenient source. Now we have source 1 and source 2. Which one is at a lower potential? That's going to change depending on the direction of current, the direction of voltage in the system. So if we need to connect the substrate to the lowest potential for reliability reasons mostly, then we need an active circuit to constantly be checking which of these two sources is lower and then biasing the substrate. So we at Infineon, we have a very advanced proprietary structure to do this monolithically on the GaN chip. So when you buy this GaN BDS, you see one package. If you look inside, you'll see one chip, but inside that chip is a substrate biasing circuit that will connect the silicon substrate to the lower potential for reliability reasons, so you don't have to worry about it at all. So now we have this 650 volt bidirectional switch. What are we going to do with it? Well, there's a few different use cases. And I like to lump them into three categories. The first is existing topologies that are already used quite often, things like Vienna type rectifiers or P-type. If you have a Vienna rectifier and you replace the diodes with active switches, you've got yourself a bidirectional P-type topology that could be DC to AC, AC to DC, or back and forth. These are very often used in AI servers and in lighting. In onboard chargers, you would also see topologies like that. But what we're seeing there in a lot of onboard chargers, as well as in some solar applications, is the adoption of something called a direct single stage topology. So this usually involves a cyclo converter or a matrix converter. And I'll get into that more later. And then thirdly, current source inverters, which is fundamentally different from these. So we have three very different use cases for BDS. This isn't to say these are the only ones, but these are the most popular ones today. So let's start with those power conversion cases. So you'll already see in the world today, if you go out and buy, let's say, an uninterruptible power supply, you'll probably see some Vienna rectifier at the front end. But actually, that's more likely to be a P-type because of the bidirectional power flow. So anywhere that you're going to see a grid-connected device, you with a high enough power level, let's say that there needs to be power factor correction, you very well may see an H4 PFC or a Vienna rectifier. Now, on the 3-phase, you also have the Vienna rectifier or the Swiss rectifier, which is similar. And then you'll also see in the solar string inverter world, you're going to see the Herrick inverter. These are all already used in the world today, but with back-to-back MOSFETs. Either silicon MOSFETs, could be IGBTs sometimes. More recently, we're seeing these a lot with silicon carbide MOSFETs in a back-to-back configuration. So here, we're not talking about a topology improvement. If you're already using these topologies, well, then it's a really great scenario for you because we can just simply take your back-to-back MOSFETs and replace them with fewer GaN BDSs. How many fewer depends. So, for example, if you have a system that is designed with 2 back-to-back 20 milliohm MOSFETs, because they're back-to-back in series, when they're on, you're going to have 40 milliohms, 20 plus 20. So in theory, you could replace those two with a single 40 milliohm BDS. And this, in terms of how much semiconductor, like chip real estate, you're using, is a factor of 4 smaller, at least. So you're going to save a lot of chip real estate. However, there may be a problem thermally. So if you were designing with 2 20 milliohm switches back to back, they were in separate packages, maybe each of them in a total T package. So it could be that that package can only dissipate an amount of power equivalent to 20 milliohms. So it could be that you have to replace back-to-back 20 milliohm MOSFETs with a single 20 milliohm GaN bidirectional switch. Now that's still a savings of 2x in the real estate, but also now you have half the RDS on. So you replaced 40 milliohms of conduction loss with 20 milliohms of conduction loss, which means you're going to have much higher efficiency. We find that in most cases, the truth falls somewhere in between. Maybe you replace those 2 20 milliohm MOSFETs with a 30 milliohm GaN BDS, something slightly higher, but not the equivalent of the overall parts, because you have to consider efficiency as well as the thermal dissipation capability. So whether you're replacing the 2 or 4, you're going to have a lower BOM cost as a result. And you have all the benefits that come with GaN. So you're going to have lower switching losses from the gate, lower switching losses from QSS, no QRR. All of these benefits we normally talk about with GaN, you're going to get here, as well as the huge size advantage you're going to have from replacing 2 or more switches with 1. But what if we wanted to talk about a different topology than what you're already using? Not the Vienna rectifier, but something a little bit more advanced. This is where things, to me, get a lot more interesting. So let's say you're looking at a traditional OBC where you need bidirectional voltage blocking and current control, meaning that you don't want, you need to protect the car's battery from the grid from the car's battery. So you need bidirectional voltage blocking. You need control over how much current is coming out. You don't want to be just indiscriminately charging the battery. You could overheat it. You could blow a breaker on your grid supply. And generally, you're going to need to support 1-phase, 3-phase, or split-phase charging, because for an onboard charger, you're going to want to be able to drive around, let's say, your continent or terrestrially, the part of the world you're in, and still be able to charge it wherever you go. And there are going to be different regions that have different types of charging ports. So that's going to look like this. You're going to have your grid. You're going to have EMI filter. Your rectifier could be a Vienna, could be a totem pole PFC, whatever, depending on whether it's single phase, 3-phase. If you're DC link, this is usually going to be very large and a lot of electrolytic capacitors. Then you're going to have an inverter that's going to create some higher frequency, let's say 200 kilohertz. Over here, this rectifier was at 50 hertz or 60 hertz, depending on the world you're at. the part of the world you're at. But this here, we want to create something high frequency because you want to use a very small transformer, maybe even planar magnetic. So here we're talking about hundreds of kilohertz. Then you're going to have a rectifier, and then your DC filter and the output. When we talk about AC to AC topologies or single stage topologies, we're talking about replacing this part here. And as I mentioned, you have a very large DC link in the middle. It's very desirable to get rid of that. It's bulky, it's expensive. Electrolytic caps are notorious for having short lifetimes. A lot of people are moving towards hybrid polymer caps for that reason, which are a lot more expensive. But the issue here is that we've got AC on the left side of this box and AC on the right side of this box. Here you have 50 hertz. Here you have, let's say, 200 kilohertz. Now is where we can look at not really a new topology, but a very old topology, the matrix converter or the cyclo converter. Cyclo for single phase, matrix for three phase. So we're replacing all three of these components with this one topology that is an AC to AC converter. It converts the low frequency AC to the higher frequency AC. It eliminates quite a lot of real estate and cost in your system, and it also can enable a much higher efficiency depending on your design targets. There's a few different ways you can slice this. You can use a single phase cyclo converter, and that's just going to be for onboard charging in a single phase. So if you're plugging it at home, for example, a residential charger. Now, if you want to be able to charge from single phase or split phase or three phase, we're mostly talking about a phase modular converter, which is something similar to three cyclo converters in parallel, one for each phase, controlled sort of independently. Or you could talk about a full three-phase matrix converter. Now, there's pros and cons to all three approaches. If we're talking about a three-phase matrix converter, one of the issues is that for these bidirectional switches, it's going to require a higher voltage rating than 650 volts. There are some options to make the bidirectional GaN switch above 650. We are, of course, working on them along with a lot of other major players in the market. But for the moment, what you'll find on the open market today are 650 volts. So here, if you wanted to do this today, you would have to use 1200 volts back-to-back silicon carbide MOSFET, which is exactly what the Cybertruck has used. And there are some citations you can see here at the bottom, some teardowns where you can see that, in fact, the Cybertruck OBC is using a matrix converter with back-to-back silicon carbide MOSFETs. Why not GaN? Well, when they did this, there were no GaN bidirectional switches in production yet, certainly not with automotive qualification. Not yet, but this is something coming very soon. As well as the fact that they were doing a matrix converter. So they were using 1200 volt switches. Now, what if you wanted to start a project today to design an onboard charger for three-phase, split phase, single phase? Well, I've got good news, because with the phase modular approach, you don't need more than 650 volts. This phase modular approach, as I mentioned, it's mostly three individual cyclo converters, each of which is only blocking the 230 volts AC or 110 volts AC, depending on where you are in the world. And this gives you full flexibility to address single phase. If you want single phase, you can put these three cyclo converters in parallel or just run one. If you want three phase, you use the three phases in a synchronized way, semi-independent, but synchronized by a common controller. Or split phase, you use two phases. So you have quite a lot of flexibility, and you also have robustness in case the three phases from your grid are unbalanced. Now, there is a third option for the three-phase, which was developed by ETH Zurich. And I have more about that in the next slide. But compared to these other approaches, you have fewer switches, especially on the secondary side, but you do still get all these benefits of flexibility for imbalanced phases, single phase, three phase, two phase. And ETH Zurich, to be honest, is one of the most experienced universities with GaN bidirectional switches. We work very closely with them, and they've been publishing work with GaN bidirectional switches for, I think, maybe over 10 years. So it's no surprise that they came up with this very advanced topology here. They call it the X rectifier, meaning extended functionality rectifier. And I would encourage you to take a look at the paper from PCIM last year. It's linked here. When you get the slides, you can take a look. And as I mentioned, this uses the 650 volt bidirectional switch and allows for full flexibility batteries from 250 to 450 volts with vehicle to grid, vehicle to load mode, handling strong imbalances with a lot of robustness. So beyond just automotive, we're seeing this single stage power conversion using cyclo converters, matrix converters, the AC to AC part. We're seeing this penetrate markets all over. So for onboard chargers, whether it's your car or your e-scooter, but even with the power going in the opposite direction, rather than grid to battery, here we're talking about battery to grid in the case of solar microinverters. This is already heavily used. There have been some talks, some keynote talks by Michael Harrison of Enphase on how strongly he believes about the GaN bidirectional switch as game-changing for solar microinverters as well as other applications. But then we even see things like major home appliances. You know, we're going to be seeing our washing machines, our refrigerators, our induction cooktops use different variations of these same topologies for more efficient, lower cost, higher power density conversion of power from AC to DC, DC to AC. Now, lastly, let's talk about motor drives. You know, this is about electrification. Electrification is more than just charging a battery. Once you charge the battery, of course, you want to use that energy to get you going, to get you where you were trying to go. So let's talk about how GaN, and especially the GaN BDS, can benefit in automotive traction inverters, or let's say generally in motor drives. So what do people use today? They use a traditional 2-level voltage source inverter. The switching frequencies are usually as low as you can get before they're too much in the audible range. And let me tell you, 8 kilohertz is a very commonly used frequency for automotive traction inverters, and you can hear it. The people younger than myself can hear it louder. And I think you might find that pets and animals can find it very disturbing. There's a lot of acoustic tricks that are played for that. So sometimes you'll find the frequency pushed a bit up to 20 kilohertz. This is out of the range of most mammals. But that's as high as you go, you know, because you're just trying to get out of the audible range, and that's the end of it. And one of the reasons is that the switching losses per event, per switching cycle, are pretty high. That switching loss is not dictated by the transistor technology. It's more dictated by the slew rate, by the overlap. If you have 400 volts on your battery and you want to commutate that at 1 volt per nanosecond, at 1 volt per nanosecond and 400 volts is 400 nanoseconds of overlap. That's a lot of I times V times time, which is going to give you a lot of losses at 20 kilohertz. You're not going to want to go higher. And why do people slow the slew rate down? It's for a lot of reasons. Honestly, sometimes it's just uncertainty. You maybe don't want to spend the time finding how high the slew rate can be before you run into problems, because you will run into problems. Let's say you designed your motor drive from the start with 100 volts per nanosecond. You're probably going to find that you're breaking down and degrading the insulation of your motor windings, this enamel-coated insulation. You're probably going to cause some pitting in the bearings of the motor due to eddy currents. You're going to find that there are a number of different issues on the cable from the battery to the motor, one of which could be standing waves from reflection along the cable. One could be radiated EMI. I mean, a long cable, if it's not shielded, is basically an antenna. And then you're just broadcasting your own TV station from that connection from the motor to the battery. So people usually are slowing that down a bit. It probably can go higher than 5 volts per nanosecond, but how much higher depends exactly on the architecture of the system, the length of the cable, a lot of things. Now, you can switch at a really high frequency. Let's say you wanted to switch at 500 kilohertz. If you do that, you can apply a low-pass filter between the inverter and the motor. Then the motor and the cables don't see that DVDT, so you could go as fast as you want. You could switch at 400 volts per nanosecond and then go to really high frequency and filter out. And this is called a sinusoidal output motor drive, or a motor-friendly drive, because it's, of course, much more friendly to the motor if the motor doesn't have to filter out all of the switching noise itself. This is rarely used, mostly because you have 3 quite large inductors and capacitors, one on each face. One solution to this is the T-type voltage source inverter. So this is basically the same as the T-type power conversion I mentioned before. You could use T-type for your rectifier, and very often a T-type is used as the front end for a UPS, an uninterruptible power supply, because you need bidirectional power flow and it's very efficient. Now, compared to the traditional BSI, this is going to help you a bit with the DVDT limitations, because you're only going to be switching half the voltage. So if you have a 400 volt battery, you're only switching 200 volts every switching event. Because the voltage you're switching is lower, the current ripple is lower. That current ripple is going to reduce your losses in the motor. It's going to reduce your losses in the capacitors and the ESR of the input caps. So you're going to have better efficiency because of this lower current ripple. You also have the option to toggle between 2-level and 3-level mode, meaning you can just turn off all these bidirectional switches. Or in this case, what I'm showing you here are back-to-back MOSFETs, but you can use your imagination that this could be bidirectional switches here. If you turn them off, you can operate it just as a normal 2-level BSI. This gives you a little bit more room to optimize for efficiency over the full load range. Certain load points you're going to want to run as a traditional 2-level. Other load points, maybe you want to engage the BDS stage and switch with 3 levels. And here also, because it's multi-level, you can use 650 volt rated bidirectional switches for these horizontal legs here, and still run with an 800 volt battery and apply 800 volts to the motor, because they're only switching half that voltage. So these switches in that case would be 1200 volt SiC MOSFETs, and you have the 650 volt bidirectional switches here. So this is a very interesting direction for traction inverters. The third option for the traction inverter would be the current source inverter. This is a little bit more next gen, although there's been literature about it for many decades, using back-to-back MOSFETs. But in this case, we're showing you a visualization with the GaN BDS. There's also quite a lot of literature from ETH Zurich and other universities. University of Wisconsin is a notable one. They find that the current source inverter is useful compared to these other approaches for a number of reasons. One is you don't have to worry about DVDT at all, because the output is a filtered current mode output going to the motor. Now, also for this reason, you can get rid of electrolytic capacitors. Your energy storage in this case is not done by a capacitor, but rather it's done by this one inductor. Now, I just mentioned that people don't use this filtered sine wave output BSI because of the inductors. But keep in mind here, we're talking about only one inductor, not 3. So, and we're talking about eliminating the electrolytic capacitors of the bulk. That's very nice. It's very, very helpful. It offsets that cost and size of the inductor. It's inherently protected against motor phase short circuit. And this is a big issue in inverters, to be prepared in case there is a short between windings. The windings are typically this enamel-coated stuff that can break down over time. And then if you have a short inside the motor, then the inverter needs to be fail-safe. The current source inverter is inherently fail-safe there. And lastly, you have buck and boost functionality from the battery. So the VSI is essentially just 3 buck converters, right? It's bucking down. It can apply to the motor any voltage up to the battery voltage, but nothing higher. This leads to some special tricks to get to very high speeds beyond the normal capability of the motor using flux weakening. Here, you don't have to worry about that because you have a buck stage here at the input, and then each individual motor phase is essentially acting as a boost phase. So you can apply to the motor even higher voltage than you have in the battery. This allows for you to optimize the voltage you're applying for the full load profile that you're trying to target across speed and torque. So now's the time to wrap up. I think I've thrown a lot of information at you, and I'm hoping for some really good questions. I would summarize by saying this is not about what's coming in the future. This is about what's here now. We already have in mass production the battery protection switch that I mentioned at 40 volts. Other voltage nodes will be coming soon. We have the 650 volt bidirectional switch in mass production already designed into end customer products that you may even have in your house today. There are huge improvements you can see at the system level: size, efficiency, cost. But what I would ask to you to think about is, what do you think the next killer app is going to be for bidirectional GaN? Because most of us in this field have spent the better part of our career designing around unidirectional switches, as if that's all that there is. We have diodes, we have MOSFETs, we have BJTs and thyristors, etc. But now we have a new tool in our toolbox. So what's next? Who's going to dream up what comes next? I hope that it's somebody in this call. So the challenge has been thrown down. With that, I'd like to conclude and open it up for questions. Valentina, you're muted.
Sorry, thank you. So we have a couple of questions, and the first one is, how difficult is the gate driving? Is there a challenge to driving BDS?
Yeah, it's a great question. Let me go back to that slide. So in fact, for the common drain BDS, it's no problem at all. You have gate 1 and source 1, gate 2 and source 2. You connect each one exactly the same gate driving circuit you would apply to the normal gate and source in a unidirectional GaN HEMT. In our case at Infineon, we use the gate injection transistor, which involves a few extra passive components. But you would just use 2 of those. And if it's a Schottky gate GaN HEMT, then you would use 2 of those. There's no complexity whatsoever.
Okay. And do you expect that the GaN BDS adoption to pick up sooner for onboard charging in electric vehicles, or do you think the motors drives might happen first?
Well, it's really hard to say. I did mention that the Tesla Cybertruck already uses a matrix converter. So at least on the topology side, there's a head start for the onboard charger. And I think that we will probably find that any of us that go out and buy a new electric vehicle in 5 years, it probably is going to have bidirectional switches, GaN BDS based onboard chargers. The momentum's already there. Okay. But that being said, the T-type traction inverter or the current source inverter could come along really fast and surprise us all.
Okay, the last one. How long have GaN bidirectional switches existed in the market? Because they sound very new. And there are any other applications that are already using the GaN BDS outside automotive?
Yeah, so I mentioned before about this, I think it was, I don't remember if it was APEC or PCIM last year in 2025. But Michael Harrison from Enphase gave the keynote speech. And I think they've been pretty public that they are now using GaN bidirectional switches from Infineon, as well as others. I think they have a multi-sourcing approach, so we're not the only ones. But they are using this in their microinverters for rooftop solar. So this is already out there. If you just had an Enphase-based system installed on your roof, they may have some GaN bidirectional switches inside.
Okay, so thank you, Edward. I don't have any more questions right now for you, but I invite and I encourage all the attendees to basically use the Q&A box, and we can basically answer in the chat after the session. So thank you for attending this session, and please join the next section from the lobby.